My name is David Dominguez. Part of the team is Gianni Jimenez and Genesis Vasquez. And we are Team 10. Our advisor is Dr. Louis Brivich. And we are doing a reaction control system for NASA's NanoLaunch project. Now the goal of the NanoLaunch project is to build the cheapest launch vehicle that can get a 3U CubeSat into orbit. And the motivation for that is to try to get more universities to be able to do space experimentations so they could do global observations and atmospheric studies whose results can help the world as a whole. Now, besides being cheaper, NanoLaunch, right now, these vehicles, very expensive vehicles right here, are the only ones that can get a CubeSat into orbit. And besides the cost, the scheduling is very difficult because they might be going to a different altitude, different inclination. They might not even have a CubeSat deployer on board. So the NanoLaunch, which is this little rocket right here, is 5 stages of solid rocket motors, 3 of them off the shelf, 2 of them that NASA's developing. And it needs a reaction control system. So in the top 2 stages. So the purpose of the reaction control system is that since there's no atmosphere in space, you can't use fins, so you need some kind of propulsion. And before you fire each stage, you need to align the rocket for the proper pitch and the proper orientation for the inclination to get into the right orbit. So here it shows you kind of how the space shuttle uses the RCS to, for direction control. And so it functions as pitch and roll. And so here you can see it launching out of wallops, which are going to launch, and the RCS activations are going to happen between the stage operations.
All right, thank you, David. So here are our objectives. Our objectives are to design a reaction control system that's reliable, it's at a low cost, easy to manufacture, and safe. And we plan to build and test a prototype. First, we're going to do some computational fluid dynamics to make sure that our valve is moving the air where it needs to go. And we're going to perform some rapid prototyping in order to have a physical model to test. And then we'll do some dynamic analysis once we test the model. And we're currently collaborating with NASA. They're providing funding. They're also providing the needs, goals, and objectives for our project. So we're working towards their directives. We're also collaborating with the Maid-Rock Laboratory, and there's experts on computational fluid dynamics that will assist us in this endeavor. And here's a small breakdown of responsibilities. So David and Johnny will work on the CAD design, manufacturing, and testing, and then me and Johnny will collaborate to do the analysis and dynamic analysis and also the specifications. And here's a short timeline of how we plan to split up the work so that we can have everything done this. The NASA group is already creating their own prototype, and this is a picture of what it looks like right now. This is their CAD model, and this is their physical product. And it has a number of disadvantages, though. It has a lot of pipe fittings and a lot of valves that are very expensive and leads to more failure points and higher weight and cost.
Okay, so this is our final design as of now. We came up with this idea where we're going to have a rotating valve system. NASA wasn't impressed by it. David came up with it. He took it to them, and they told them basically, go ahead and build it up, and we'll fund you. Some of the design challenges we have to analyze and overcome includes the force that is going to be exerted on the valve, on the bearings, on the back plate, and the screws that's going to hold the system together. We're hoping to build 3 prototypes. One is going to be milled out of Delbring. Security was helpful enough to give us some input on the manufacturing and tooling tolerances. We're also going to 3D print 2 of them. One is going to be 3D printed here out of PLA. And if the system is feasible, NASA will go ahead and 3D print one out of titanium for future test vehicles. As you can see, that's the manifold, the valve inside, which is going to rotate. And the next slide. Now, one of the advantages of our system is that it only uses one on-off valve. NASA uses 4. This will allow us to use less pipe fittings and less pipe materials. One of the disadvantages we have to consider is the stepping motor, the stepping motor that controls the valve. Now, our system will go ahead and meet the requirements set by NASA to have 4 different activations for controlling the rocket.
And our current products, we're currently finalizing the valve design and the tube layout, and we're running some preliminary analysis. have already been sourced, so we know exactly where to go for our future steps. And we'd like to thank Dr. Milukavich and the Maynard Lab, and also Dr. Sigmund.
Any questions?
I got,
Sorry.
go ahead. I
Can
got
you show your cost analysis?
I got none.
Okay.
The timeline was one of my big things. You got it. Very good job.
Thank you.
As for the cost analysis, we've been sending stuff to NASA and just build it and send it back to us. So,